Hello everyone. So in this recording, I'm going to be talking about hashes and digests, right? The hash function or a hash function is a mathematical transformation that we use to take a, a message of any length and transform it into a message of fixed length, right? Which usually short, right? And there are many applications for hashes and message digests. We actually looked at some of them before, especially in authentication and integrity check. But we will look at those later, right? So, but we have issues with this. So intuitively, if you take a message of any length and shrink it into smaller message size, right? Then it makes sense that there may be more messages of the same large length that they can shrink to the same length, right? So or the same hash. So let's take an example. Let's say um, um, we are representing the hash function with h, right? Um, and if I take the hash here, we end up with d, which is the output, right? Let's say the output is, hypothetically speaking, 4 bits, right? 0, 0, 0, 0, 0, 0, 0, 1. We have 16 different ways or 16 different symbols that we can generate using 4 bits. But the messages out there are infinite, right? So any one of those messages, the arbitrary length message, can go into one of these 16. So obviously, there there are out there some messages that can end up with the same hash. We call that a collision. The solution for the collision is to make or reduce the amount of collision uh, we need to make n large. So 10 to the power of 4, that's 16. That's very few. But if I make n 64-bit, then we have 2 to the power of 64 different hashes. So the possibility of two messages colliding is reduced. If I make the n256, the possibility of collision is even less, right? So that's one property of the hash. We take any arbitrary or any length message and reduce it into a fixed size message. We will call this one-way function, right? We call it one-way function because usually the transition from a message here to the hash here is easy. But the reverse is almost impossible. So as I said, there are infinite number of messages out there. They all go uh, and shrunk can be shrunk into a fixed size message. But if I want to go back, which one of those many possibility of messages had was the original message? It's very hard to find, right? So the inverse here, taking the message from the digest is very difficult. It's not impossible, but it's very difficult. And all the hash algorithms that we are gonna look at, they try to find a way to make this possibility very slim, right? So we don't have uh, uh, many ways to take a hash and find the original message that generated it. Okay, and obviously any attacker, any hacker will try to do the opposite, will try actually to find the message that generated the hash. So if somebody created a message and then found the hash to it, right? That's M1. The hacker will try to find another another message, not the same one, but another one that generates the same hash, right? So in this case, the hash of the M1 equal the hash of the M2, and that's the collision. We want to make sure that this possibility is small. Okay. So let's take a look at a simplistic hash function. So in this table that you see before here, we have two numbers, and the two numbers are different. Right? And let's say we add to each number, this is our hash function, add same 677888 to both sides, and then take the 6 digits starting from digit 6 or digit 6, yeah, the 6th, the 7th, 8th, 9th, and so on, right? So this becomes our hash 612673, and the second is this one. So now this is a simplistic example of taking any number and getting the hash of it. Now from this example we can see that there are many ways. Yeah, it's rare that we have a number, add another number to it, square, get the square, and take the 6 digits. Probably we won't have many numbers that are generating the same hash by following this example. Right? But it's not possible. It's not impossible to find two numbers that can generate the same hash, especially with this simple example here. All right, so let's take a look at some of the applications. Right. So one of the main applications for hash and digest is the authentication. And we saw authentication before. We saw actually different examples of authentications in secret key cryptography, in public key cryptography, and here in the hash. Also, we can use the hash for authentication. So Alice sends a random number to Bob. Bob sends back the hash of the random number plus a key that both of them agree to. Okay? Now, because this is a one-way function, Alice has no way of reversing the process, right? Not like the security, the encryption before, where we can decrypt the messages. Here, there is no way we can decrypt the messages. Hash functions don't have keys. So the key here is just a number that both of them agree to, so that they can concatenate it with the random number. But Alice can do the same process, can take her random number that she knows and attach to it or add to it the key that Bob and Alice agreed to, take the hash of that and compare it to the hash that she received from Bob. If both hashes the same, then he must be Bob, right? So let me repeat that here. So Alice, Bob, and by the way, we call that keyed hash. Not all hashes are keyed, so there is no key or non-key hash, and there is a hash, and they work the same. Anyways, we can use them the same way. So let's take this example where Alice and Bob agree on a key or a message, that a phrase or a password, right? Um, Alice sends, well, wants to authenticate, wants to make sure that Bob is actually Bob. So she sends random number. Bob take the random number, attach the key to it, and hashes both, and sends the result to Alice. Alice cannot undo this, right? But she can do the same thing. She can say, well, I'm gonna hash R and K, right? And compare it to whatever Bob sent me. If they match, then actually Bob did it. The same process, we can do it again without the key, right? So we don't have to exchange the key really. We can send R and send back. So we call this the no key hash. So we can, and Bob can send uh, R. The only problem with this approach is that um, if somebody knows the algorithm of the hashing, they can do the same thing. They can hash R even if they are not Bob. Um, so this system works in different applications. It works, but in different applications where we don't share R and HR on the same channel. Okay, so that's the authentication. How about another application, which is message integrity? So here we saw that before with the Mac or MIC, where we send a message in plain text, but we also attach um, a message integrity check or checksum or anything like that, encrypted, so that we know that nobody changed the message along the way. So same concept. We take a message and we take this random number or key that both Alice and Bob agreed to, and we hash it and we send it with the message. So H1 plus the message. Bob receives the message and the hash, and Bob wants to make sure that the message actually not didn't change in the way. So Bob cannot reverse H1, but it can calculate H2 with taking the message and the key that both agreed to, and he hashes them. And if H1 and H2 are the same, then Bob knows that Alice's message was unchanged on the way. Again, we don't have to have, in some applications we don't need to have a key, right? Um, but this is the more general approach where we have a key shared between Alice and Bob. Another application for hashing is the password hashing. So with the password, we know that um, when we register for a website or when we yeah, I mean, we buy something online or we register for any service. Sometimes we're asked to put our information, username, address, and the password, right, as part of the registration process. So the password must be stored somewhere, right? But storing it in a file so that when the user comes back and put the password again, is risky. If I store a password in a file in the server, somebody may compromise that server and steal all the passwords. So we want to have a way that we can store the password without actually storing it in clear text. So what can we do? Well, hash can be used in this process. Now remember, for this to work, messages should not have the same hash. So M1 with and M2, they shouldn't we shouldn't have two messages that share the same hash. Otherwise the system won't work, right? So how does this work? Um, so the user registers by putting their info, username for example, and password. So the server does not save the password directly. Instead, they save the hash of the password. Okay, next time the user is trying to log in, so this is the registration. And this is the login. So the next time the user tries to log in, they will put username and password, right? So now the server does not have the original password. It has the hash of it. But they can calculate H1 of the password, and then they compare this with all the hashes in the file, or actually they compare it with the username, with the hash of the user, not all password. All right, so if these two are the same, well, we know that the possibility of two hashes being the same generated by different password is very, very, very slim, right? So if these two H1 and H match, then the user must have saved the password or put the correct password. So this way we don't need to store the actual password. We just need to store the hash, right? All right, so what if somebody get their hands on the hashes? Will they be able to figure out the password? Not really. It's very hard um, to find the password that generated this hash. And to make things even more difficult for anybody, let's say two users by coincidence put pass 123, pass 123, right? So in this case, their hashes will match because the password is the same. So the server sometimes they put something called salt. Salt is an extra information here, or an extra random number that makes sure that even if the user put the same username or the same password, this number is different for both of them, so the hash will never be the same. And also, this makes it difficult for an attacker to guess passwords. The, the, the attackers may guess some password. So they may try different dictionary names, different dictionary words, and find what the hash is for them, right? So that makes it even more difficult for the attacker to do the simple attacks like that. Okay, and another application is what we call the message fingerprint. This is really useful if I want to make sure that files I store in a file system are not changed while I'm not looking or I'm not aware. So let's say I'm saving a backup for the configuration of a router, right? And that's the most reasonable thing to do. I keep configuration backups in my file system just in case a router fails and needs to be reconfigured. So I go back to the backup and update the router or any device. But that actually makes the file in the file system or the configuration of the file system vulnerable to attacks. Somebody may go to the file and change some of the commands, change some of the instructions in the configuration file. So when I update the backup, I think it's the backup, but it's actually something that was changed, right? And that applies to any file, not necessarily backup, but any file. So how do I make sure that this file that was stored, nobody changed it? All right, so in that case, I will save the file and I also create a hash of the file and I save it alongside the file. Somebody make sure that, or somebody go and to the text file and change it. So next time I try to use that file, I can do the hash again and compare the hash with the hash that was saved before. If the file was changed, the hash will not match, and I will know that the file has been tampered with and I discard it and don't use it. And I can do that periodically, so to make sure that, not just before I use the file, but maybe every 24 hours I go through all the files in the system, take the hash, and then compare them with the hash that I already saved. And if there is no match, or if they don't match, I know that this changed. And this technique can be used also not for to protect against malicious attacks, but also to see if a file was edited, right? Not necessarily bad thing. So if I want to know if a file has changed or edited or two different of the files, I have two copies and I want to make sure that, or I want to know if these two copies are identical or they are different. So instead of comparing word by word or letter by letter, I can take the hash of the two files and compare them. If they don't match, I know that the files have been edited, right? And it can be used for version control as well. So it has many applications. The only catch here is that if the hash function is well known, the attacker can change the file and change the hash as well, right? The attacker have access to the file, so they can change the file, use the same hash function, and save the hash as well. So they fooled me twice. They fooled me by changing the file, and also they changed the hash. So in that case, I have to make sure that either the hash is in a separate file system, so the hashes will be somewhere else, so the attacker won't get hold of the hash, or the hash function itself is secret. So the hash algorithm is something that only I know about, right? Either way, we prevent the hacker from changing both systems together. Right. Okay, so I talked a lot about the possibility of a collision, possibility of two messages having the same hash. We don't want that. We want something that's um, very or close to immune to that possibility, right? So to study the possibility of two messages having the same hash, we will use something called birthday problem in probability. And it's actually very simple and nice problem. We should have studied it earlier in the first chapter, actually. But I left it to here just so that we understand its applications in more practical terms rather than just studying it in abstract. Right? So the problem says simply, if we have a classroom of n students, right? What is the probability that at least two students share the same birthday, right? So let's assume that birthdays, we have 365 days a year. Forget the leap year, but let's say 365 days. And let's assume that the birthdays are split evenly or distributed evenly or uniformly across all days. So the possibility of being born on January 1st is the same as the probability of being born on January 7th, same as the probability of being born on October 25th. So, right now, these two are probably, or the last assumption is probably not entirely true, because statistics say that people are born in certain months more than others. But anyway, to understand the problem, let's assume that uh, being born in any specific day follows a uniform distribution, so all probabilities are the same. Okay, so in this case, how do we know what is the probability of having two classmates sharing the same birthday, right? Okay, so let's take a look at the inverse of this problem, which is easier to calculate. We'll try to find the probability, or our attempt is to find the probability of two or more students share same birthday. This is, from what you know, is 1 minus the probability of no students share same birthday. All right. So this one, let's call it Pn for simplicity. So n here represents the number of students in the classroom. So how do we calculate that? Let's assume that the class has one student. Now the probability of class of sharing birthday with somebody else is 1, or the probability of not sharing the birthday with anyone else in the class is 1, because it's just one person, right? So that's, let's say, this is 1 means k over k, where k is the number of the days in the year, right? We could simply say just 1, but you understand why I'm doing it this way. When we have another students, so the other students come, right? What is the probability that students will not share the same birthday as the one students who came earlier? Now, the first student was born in one of the days out of 365. So there are 365 or 364 days left for the other student to be born in without clashing with the first one. So the probability of the students not sharing a birthday with the first student is k minus 1 over k, right? Or I can write it as 365 over 365. That's the first case. And the second case is 364 over 365. So the probability of not sharing a birthday with the first students is 364. How about we have third student coming? So the third student comes to the class, and now they have 363 ways not sharing a birthday with either one of the first two. So that's k minus 2 over k, right? So this continues until we have n students in the class. So the last student will be k minus n over k. If I simplify this, this is equivalent to k minus the denominator is k factorial divided by k minus n factorial, and the denominator here is 1 over k to the power n, right? Because we have 1, 2, 3 up to n here. So that's the solution for the probability of no two students share the same, or no students at all sharing the same birthday. So if I go back to my original probability here, so 2 or more share, this is 1 minus k factorial k minus n factorial k to the power n. Alright, somebody will say, okay, now how is that related to the collision that we talked about, the messages that we talked about? Now imagine here the messages that we have are k. We have 365 messages out there, like, right? And the n is the number of attempts to find two messages that share the same, or two hashes that share the same message or came from the same message, right? So we can use the same problem to solve the collision. Now, k factorial, as we saw earlier chapters, the k factorials and k to the power n when n is large, and they may result in really huge numbers, and finding the probability will be difficult. So there are many approximations to the birthday problems. One of them is, it says here that len p, the natural logarithm of p, is approximately minus n squared over 2k. And there are also other approximations that we will look at later when we talk about some of the tutorial questions. All right. So just back up a little bit and see here, if anybody who wants to try and find two messages that share the same hash, they have to try about 2 to the power n divided by 2 messages, where n is the number of bits, right? So if I have, my hash is four bits only, 4 bits, which is ridiculously small, but if we have the hash is 4 bits, it will take somebody 2 to the power of 2, which is 4 attempts to find, on average, to find 2 messages that generated that hash. But if my n, the hash, is 64-bit, then it will take about 2 to the power of 32 different attempts on average to find two messages that have the same hash. Okay. So obviously, the larger the n, the better uh, the chances of having no collision. And just to note here that when we are saying attempts here, we don't really need to know what is the original message, right? So the original message we don't care about. We just need to find another message that have the same hash. So somebody wants to change uh, a content of a file, right? And the file was hashed. The file, first of all, the content itself may be plain text, so they may see it, right? So they're not going to try to decrypt it. They can see it. The challenge will be how to modify it, but in a way that the hash will stay the same. So that's what we are looking for. So we may change a message here, may change a number of a bank account, or change a value of the money that we want to withdraw, right? And then change some other random bits of data and try and try and try until we find the hash that matches the original. So uh, that's uh, that's sometimes what we want to do, and we actually the hacker wants to do, and we want to avoid. Okay, so we are going to look at two groups of hash algorithms here. The first one, um, it's a group of the message digest 2, 4, and 5 algorithms. So MD2 was the original, and it takes any number of octets and produces 128-bit message. So here, when we look at these algorithms, we need to know what is the output size, right? So they differ in the output size, and they differ also in how they handle the message, the original message. So the MD2 takes the message and break it into blocks of 16 octets. 16 by 8, by the way, is 128 bits, right? So they try to block it into 16 octets, 16 bytes. But the message sometimes it doesn't match exactly 16 bytes or multiples of 16 bytes. So the algorithm adds padding, adds probably zeros or any number that pads so that the length will be exactly multiples of 16 octets. After that, it will add another 16 octet quantity as a checksum to the end of the padded message. So you see here the message and then padding these dashed or dotted area, and then we add checksum. So now we have blocks, multiple blocks of exactly 16 octet each. We will pass them through the hash function. The hash function itself, we're not going to worry about that much, but it has multiple iterations, and it takes a block, 128-bit at a time, and initial vector here, and generates 128 block. The 128 block, or the 128 output of the hash step, is hashed with another block and another block and another block until we get the final hash. As we saw before, we could make sure that the initial vector is zeros, for example, right? Or we could have a fixed number or random number. It's just we need to initialize with some number, right? So because of these hash functions here, we the output is always 128-bit, no matter what the length is, because we are taking a block, an initial vector, and generating 128, and so on and so forth. So the output will be always 128. MD4 came later, and it came when the CPUs were more advanced and they can handle 32-bit words instead of 16-bit. So it is more of a 32-bit word oriented rather than 16-bit. All right, so and it generates the the hash using similar way, but we have a difference here in the way we pad it. So we need to make sure that the message is broken into multiples of 512 bits, not 128 like before, but 512 this time, right? Okay, so to do that, we take, let's say, if we start with something less than 512, let's say 486 as an example, right? So that's the original message, and we want to make sure that it's multiples of, or a multiple of 512. In this case, since we started with 486, so we want to make sure that it matches 512. Okay, so we start by putting 1 and 0, 0, 0, 0, 0 up to the last 64 bits. The last 64 bits are reserved to put the length of the message itself. So here with 64 bits, so that we put the number of the, or the length of the message. So if I want to calculate that precisely, I will say, so we have 486 here plus 64. Oh, actually that won't work because it will exceed 512. All right, so in this case, I have to make sure that this is twice. This is unintentional mistake, but it saves the purpose of illustrating how I want to make sure that it's multiple of 512. All right, so now 550, right? So the length here has to be 2 512 minus 550 to make sure that the whole message is exactly 2 blocks of 512. Alright, so this means that we have 1024 minus 550. So we will fill 474 bits here. So the first bit is 1 and the remaining is 0, 0, 0, 0, 0. Right? If I want to go back and rework the example with something simpler, let's say we want 512. And here instead of 486, let's say it's 386. So we need 64-bit here for the length of the message. And we have 386 here. So we want to find what is the size of this padding here. Alright, so in this case it's 512 minus 386 minus 64. So we have 62 bits that we fill here. Right? So in the first case, we want to make sure that it's multiple of 512, so we want to enlarge it to 2 blocks of 512. In the second case, 1 block will be sufficient. Of course, the 64-bit at the end um, is representing the number of bits in the unpadded message. So here it will work as long as we have, so this number here, we can take anything from 0 to 2 to the power of 64, or 64 minus 1, right? So 386 will be represented easily in binary here. 486 will also be represented easily in binary here. But if the message is actually way too long, more than 264, 2 to the power of 64, so we need to take the length of the message, this one, the L, mod 2 to the power of 64. So we make sure that the output here is always smaller, L prime here is small enough to fit inside this field. Right? Okay. The output, however, is 128-bit. All right. So we take any length message, make sure that's multiple of blocks of 512, and then we do the hashing, and we end up with 128-bit. The MD5 is designed similar to MD4, but it has more security strength. And here it says that make 4 passes instead of 3 inside. This is refers to the operations inside the H function here, right? So it's similar to the rounds that we talked about in cryptography, in the secret key cryptography, where we pass things over multiple times in rounds. So something similar, although the actual algorithm is not available to me, but the general idea is the same or similar. So the MD is considered by today's standards weak, despite generating 128-bit message. We still, thanks to the high-speed computers, it's still possible to find two messages that have the same hash, which means finding a collision. Okay? So in fact, that I was looking into some information, and one of the interesting facts is the person who broke or prove that they can find the collision for MD. He worked on creating the secure hash algorithm, or the SHA-1. So this one, which is proposed by the National Institute of Standards, the American. So this hash algorithm takes a message of up to the power of 64 bits. So it's not any length. It has a maximum length, and produces 160-bit output, which is more than 128, which means less possibility of collision. It's slower, but it's more secure. The padding works the same way as the MD4 and MD5. The only limitation is it doesn't have, the message cannot be more than 2 to the power of 64. But if you look at it, 2 to the power of 64 is not a small message. It's a huge, right? So you may hash the entire computer RAM if you want to, and without even getting into 2 to the power of 64 bits. So even though this is a theoretical limitation, but it's not a practical limitation. And in terms of passes, it does rounds for five rounds instead of four in the MD5 here, so it's 5 rounds. Then came SHA2, and this one has interesting variations. So there are multiple flavors. The first flavor is called SHA 256, and it produces 256-bit message digest using 512-bit block. The 224 is the lighter version. It produces 224-bit messages or 224-bit messages using 512 blocks. So they share the same block size, but the output is smaller. Output is smaller means probably less memory when we transmit the hash, less memory when we save the hash, and faster to produce. But we probably lose what has higher chance of collision than the original, right? The 512 take the 512-bit block and it takes 1024-bit block and produces 512-bit message, right? And the SHA 384 takes 1024-bit block and produces 384-bit digest, right? So you will see here that the same algorithm can be used for different variations, depends on the application. If I am concerned more about collisions, I will make the message longer. If I'm more concerned about memory or efficiency of communication, I'll probably use something that uses a shorter message, shorter hash. The only so the things that you need to remember out of this, first is the concept. Second is the data block. How big is it? How big is the data block? Is it 128? Is it 512? Is it 256? Is it 120, 124, 1024? And also the size of the hash itself. So each one of these have a different block size and different message size, the hash size. And also I want you to know about how to do the padding for each of these. So that's all. It's a short chapter. Most interesting part of it is understanding the birthday problem and how to use it to find out the possibilities of collisions. So that will be left to tutorials. There is a Python library called hashlib where you can try to generate different hashes for using MD5 or using SHA1 or SHA224, which is SHA2, right? And also, if you notice that sometimes when you download a free software, there is them or anything actually being downloaded from the internet, there is the hash given separately. So you can, if especially in Linux, you can take the software that you got and to make sure that it wasn't tampered with, you can hash it and compare the hash that you get with the hash that was given in with the software, right? So if the two matches, you know that you downloaded something without being, being modified. So And you can use the hash also to uh, very quickly compare two items or two objects if the two objects are big and you cannot compare them value by value or letter by letter, so you can compare them by hash, right? So that's uh, that's all we need to talk about. And if you go back to the digest, the applications where the digital signatures, we talked about message digests and generating hashes. So these are the hash functions that we use, right? Um, with the public key cryptography topics that we talked about, both are useful for um, digital signatures. Okay, so that's all. And thank you for listening, and I'll talk to you soon.